recording. So as I mentioned, so this session is going to talk focus on the static stability. And I hope you you still remember what we have discussed a few times, well, some weeks ago, as well as also in aircraft system and avionics, about the conventions or the notations that we use. So I hope you still remember. If I could just move it. Sorry about that. I should show that. You can, everybody could see this. Let's delete that. This is accidentally. Okay, so I hope everybody could still see this and then still remember, right? So the conventions I mentioned about the notation is about you need to bear in mind that in terms of motion, you have translational motions in X and Y and Z. Obviously, the aircraft is moving up and down, forward and backward, obviously, and also sideways. It could move sideways in a way that we talk about stability later on. Now, the conventions of notations that we use, for example, so that you know that this is already about the three Euler angles, we call it, pi, theta, and psi, which is roll, pitch, and yaw, and then the angular rate of it, which is P, Q, and R. But of course, in terms of forces and moments, Lm and N. Now, later on, we mostly talk about is aerodynamic derivatives. So I don't want you to get confused when we say about, for example, aerodynamic derivatives of rolling moment. Usually we call it at C with a small l. And then when we talk about coefficient of pitching moment, which is obviously C with the subscript m, small m, and obviously later on, when we talk about coefficient of yawing moment, this is C with the subscript n, which is small n. Okay, now then don't get confused about, for example, like CL here with the C and the subscript L, which is small letter L, with obviously we always talk about C, another aerodynamic derivative, which is a lift coefficient, which is C with the subscript L, capital L. Okay, so but when you talk about stability, you could also simplify that in terms of analysis. People always make simplifications about how you look at it in terms of the motions of your aircraft. So if I could just maybe slightly smaller like that. Now, you could divide it into those 6 degrees of freedom, right? The aircraft are moving in 6 degrees of freedom. And those 6 degrees of freedom, you could divide it into 3 kind of modes, right? Now, if you look at into the sideways like this, and then you want to look into the stability in its longitudinal motion or in a longitudinal mode, then you could only have a look at the aircraft in sideways like this. Right, so if the aircraft is obviously make some acceleration or deceleration, or if actually moving up and down in terms of changing in altitude, and obviously we also talk about its moment around its CG. In this case, obviously that related to the pitching moment, right? So if you look at and sideways like this, then this is about the pitching moment. And obviously this is something to do with longitudinal stability mode, right? Now, if you look at the aircraft from the front view of the aircraft, that is your Y body axis, and that is your Z body axis in that directions. And this is about, we call it a lateral mode or lateral stability mode. Then if you look at from the top view of your aircraft, that is your body axis X, body axis Y, and then this is something to do with the aircraft motions in that direction, sideways, which is left to right. And obviously later on you will see that the aircraft also, how do you call it, slalom, like a movement, like a snaking, like that. That is related to directional stability mode. Now, some books, most of the books even, in my analysis, I usually couple them together. All right, so we could consider this as a single, like a independent analysis in longitudinal stability mode or longitudinal stability motion. But lateral and directional, you can't simply separate them. Why? I think I've told you a few times already. This is because of the adverse yawing motions and adverse rolling motion. Remember that I always say that the aircraft, if you try to roll it, you can't just simply see a pure roll because of what? Because the adverse yaw happens from the vertical tail. Right? The same if you're talking about the yawing moment, you try to deflect your rudder like that. I think it's better to make it's quite big. So if you want to deflect your rudder, you are expecting that your aircraft is only yawing in that direction, but of course, because of the conventional shape of your aircraft, that vertical tails also give you the rolling moment as well. So that's why I said in some books or in some literatures they couple them together rather than talking them let's go back to here and talk them separately, because you can't simply separate them one by one, because when we talk about lateral mode now, by default it's also affect the directional mode, and then if you talk about the directional mode, then it's also affect the lateral mode as well. That's why sometimes in books they call it lateral directional, lateral with a slash directional there, because simply when you talk about the talk about a conventional aircraft like this, then lateral and directional, you can't simply separate them. Okay, so longitudinal stability mode and lateral directional stability mode. Okay, now but we try to look at those three together later on. So lateral, longitudinal first, and then lateral and directional. But I think I will try to focus on longitudinal, because obviously in a flight sim assignment, as I said, you are asked mostly about your longitudinal static stability, as well as also in aircraft design. So we're going to look at, so the slides mostly talk about longitudinal stability, but of course in some of the slides at the back you see that we also slightly talk about lateral stability and also directional stability. Okay, so now if I just skip that, so what actually the aircraft stability, anyone have already used this? I'm going to close that. So that is your 2596, your GIS code. So I'm going to close that just to clear your screen. So what is actually the aircraft stability and control? Well, is one discipline that studies how well an aircraft flies and how easily it can be controlled. Simple as that. Or in other words, how robust your aircraft is in terms of their ability to withstand any disturbances or perturbation, in which those disturbances could affect the aircraft steady state condition or equilibrium condition. So that is very, very, very clear, right? So stability concerns the tendency of your aircraft, or how robust your aircraft in terms of the ability to return to an equilibrium condition after having been disturbed or perturbed from it. Okay, now obviously that is, if you are able to analyze that, then obviously you could improve to do something about it, and then that is something to do with the control, how well that you design your control in order to improve the aircraft performance. Now if the aircraft is stable, obviously you will reduce greatly the pilot workload. Right? So the pilot, for example, if something happens with the aircraft, it's disturbed by the turbulence, for example, the pilot will not have to, put an excessive effort to make it stable, back to stable condition. That's obviously will reduce greatly your pilot workload or pilot fatigue. And obviously, then when you try to work out your aircraft in turbulence, for example, that will reduce the effect of the turbulence or the disturbance. Now, obviously, a few could affect your stability state. Is obviously that could happen in the wind gust, if you have a gust, if you have like a turbulent air, and so on and so forth, right? So if I could just move to the next. So for a conventional aircraft, so the motivation behind it is for conventional aircraft, a steady flight or a being in a state of equilibrium is the key. So you won't always have to, your aircraft is always in steady. But it is important as well, well, as well as in the required by the certification standard. If you design your aircraft, the aircraft that you are designing at the moment in aircraft design module, for example, is a conventional aircraft, and it's also governed or always directed by the safety of that aircraft, which is written in your CS25 certification standard. So it is required by the certification standard to design a stable aircraft, right? So that is the motivation why we need to study and look into the stability of your aircraft. Now, obviously, some aircraft, I think I mentioned it in the several tutorials, some aircraft are deliberately designed unstable. For example, the fighter, the military aircraft, the fighter aircraft, which is mostly the air superiority fighter aircraft, they are designed deliberately unstable because of what? Because unstable aircraft is more agile and then have a higher maneuverability, which is the intentions of designing the fighter, right? So, but for a conventional aircraft, like commercial passenger jet aircraft that you are designing, I think it's no questions that you have to design a stable aircraft, right? Now, how obviously the unstable aircraft should be flown if it's designed unstable. Now, obviously they have to, well, the pilot needs to be helped by a set of computer. Now, that set of computer is obviously provide an augmented stability to the aircraft. It's kind of like additional stability and control in order to keep all the time continuously keeping the aircraft stable. So once in, for example, like in a dogfight, then that is relaxed, that stability will be relaxed, where the agility of your aircraft and maneuverability aircraft increase, right? Now, those obviously these conditions that what I mentioned before, being able to reach this equilibrium flight, being able to maneuver in wide range of conditions, obviously that's something to do with what we call it handling qualities, which we're going to talk about that next week. So I'm not going to talk that in detail now. Okay, so now one of the keys to analyze the aircraft stability is the aircraft equation of motions, right? So we learned about that already in a few weeks ago, I guess, when we talk about equation of motions. How well you look into the stability of it, you look into the equation of motion. Now, the easiest way or the more simple to look at it, if you use a linear model, we talk about that already as well. Sorry, we talk about that as well, about the linear model. Where you could simplify, sorry about that, the equation of motion, and by looking at that, you could also analyze the stability analysis of that. Now, when we talk about whether the aircraft stable or unstable, you want to plan, you want to plan or you want to implement the control system. One of them is stability augmentation that we talked before, which is obviously continuously stabilize the aircraft. Then with regard to that, you could also design an autopilot design, for example, right? Now, I mentioned, I think once or twice about that there are two types of stability, which we're going to look at. These sessions is mostly about static stability. So the static stability is kind of like the immediate tendency of your vehicle to return to its equilibrium position after a disturbance, right? And then when you leave it for a while, and obviously you could also look into its dynamic stability. So there are two things about stability. One is static stability, and the other one is dynamic stability. So if I could just I think I take an examples about how, if I could just use my model here. For example, if you talk about tendency of your aircraft to be stable, if you got a gust disturbance like that to make your aircraft pitching up, then your alpha angle of attack increased, and obviously your lift is also increased because angle of attack increased. Then your aircraft is considered stable if its tendency to push back the nose like that back to the equilibrium state or steady state condition, right? Now, what happened after that? Now, if it has a tendency like that, you could consider your aircraft is statically stable or it has a positive static stability, right? So what happened after that, whether your aircraft then start moving like that, whether it's going to, well, the oscillation mode like that, and then whether it's going to be converged, right? Or it's going to be diverged. It start, make a bigger oscillation, a bigger amplitude, bigger and bigger over the time. That means your aircraft is dynamically unstable. If it's converged, then it's obviously you could consider that as dynamically stable, but it, diverge, a divergence oscillation, then you could consider that your aircraft is dynamically unstable. So the aircraft could be statically stable but dynamically unstable, but of course the intention is that to make it both stable, statically stable, and as well as also dynamically stable, right? So I think you have seen this before in another examples that I put. What is actually static stability? So static stability is defined as the initial tendency, that which we have already mentioned that before, initial tendency to return back to its original steady state or equilibrium state. I think one of the examples I've shown you before in the tutorial is like a ball in a bowl, right? Or marble inside of the bowl. If you put that inside of the bowl, if you perturb that, if you disturb that marble slightly with your finger, and then obviously it will rotate inside of the bowl and then go back to in kind of like a minute or so maybe, and it will back to its equilibrium state. But if you put it on the table, for example, on this flat surface like that, if you move it in that direction, it will move to there. If you move to the other direction, it will move to there, and so on. That is what we call it a neutral. But of course, if you put it on upside down bowl like that, for example, then if you slightly perturb that with your finger, it's going to go roll down, and it's never going to be back to its original state or its original condition, which is on top of that bowl. Okay, so I hope you understand the difference between, we call it a stable, right? Or sometimes we define that as a positive stability or positive static stability, neutral static stability, and negative static stability. There's another examples of this with a tumbler like that. If you put the tumbler upside down like that, if you kind of like perturb it, not a very big force, obviously, then obviously it will tend to return to its original condition. But if you put a tumbler, that tumbler is on in sideways like that on side on its sides, and obviously if you move it, it will maybe rotating around, but that is what we call it a neutral. And of course, if you put the tumbler in its perfect conditions like that, but if you see, it's very easy to be tipped over like that, and obviously that's never going to be returned to its original conditions like that. That could we could consider that as a unstable or negative static stability. Okay, so now how the aircraft is actually when we talk about the aircraft, how that is actually applies to the aircraft. Now this is related to the next slide, I guess. So we're going to look at that slide before, but obviously in the aircraft, the conditions of equilibrium state is, for example, if your aircraft flying nicely in a steady state trim condition. Okay, so if I could just put so in this steady state trim condition, then suddenly, as I said, you got a turbulence that introduce some form of static imbalance. Then it will slightly change the flight attitude. Now, in this case, if you're talking about only looking into longitudinal motion, is only change your alpha, right, angle of attack, will obviously then change the distribution of dynamic pressure. So for those of you who learn hydrodynamics, knows that if you change the alpha, then obviously you change the lift as well. Then change the lift, you change the imbalance or equilibrium forces happens in your aircraft, right? So there will be a delta lift arise from your wings there. Now, that will have a different aerodynamic forces act on your vehicle, which is obviously then perturb or disturb the equilibrium conditions of your aircraft. Right. So if you look at this illustrations, obviously, if you are in the state conditions like that, this is your original condition. For example, we look at into 3 different conditions. Then if you disturb with the gas, then your aircraft slightly nose up like that, and then there will be an alpha, for example, increase. Now, if your aircraft obviously is statically stable, then it will have a tendency forces to push it down like that. Then obviously it will then reduce the alpha slowly, and then eventually it will then make back to its original condition, which is that condition. But if your aircraft is statically unstable, then when you have an equilibrium flight like that, and then you got a disturbance, your alpha increase. If you don't have a static, your aircraft is unstable, don't have any static stability longitudinally, then obviously that alpha becomes bigger and bigger, and obviously it will tip over your aircraft in that directions. So that aircraft is obviously considered as unstable, statically unstable. But of course, there will be a condition where you're initially in equilibrium flight, and then your aircraft is disturbed, your alpha increase your angle of attack there, but your aircraft will stay in that directions until something done by the pilot, either to push it back downward by pushing the joystick or pushing the control column. That is what we consider that as a neutral static stability. So I hope you understand the difference between the, among those 3 conditions: statically stable, or positive static stability, or statically unstable, or negative static stability, or neutral static stability. Okay, now just an intro about dynamic stability. I think I already mentioned that there will be 3 types of oscillation. If the oscillations are damp, which is a converge or convergence oscillation, that we consider that as dynamically stable. But if it stays, the amplitude keeps staying without showing any divergence or convergence state, then obviously that is what we call it a dynamically neutral. That could happen, by the way. If the oscillation increases with time, the amplitude is growing and growing, and obviously a divergence oscillations, that is obviously when you say that is dynamically unstable. So that is dynamically stable. That could consider as a neutral dynamic stability, and that is what happens if your aircraft is dynamically unstable. Okay, right. Now let's look at the longitudinal. I hope you understand now longitudinal, lateral, and directional stability. Well, if you look at the longitudinal stability alone like this, now if you have an aircraft, obviously a conventional aircraft typically or must be designed to be statically stable, okay, in all of flight phases. Now, if you look at the trim conditions during cruise, if you got a disturbance like a gust like that, and then that pitch up moment due to the gust happens, and then your aircraft is obviously, if where the CG is over there, where your aircraft weight is, and then your aerodynamic centers of your aircraft. Look, we're talking about aircraft's aerodynamic centers, not only your wing, but the whole aircraft aerodynamic centers. It happens to be there, and obviously when it's a gust disturbed like that, then obviously you have an increased angle of attack, as we understand before. Then your lift increase, then that lift, if that positions like this, and obviously you can see there is a distance between the lift and the CG, then that lift will give you a rolling movement in that direction, which is a positive rolling moment. Sorry, negative rolling moment. Sorry, pitching moment. Time out. So that is a pitching moment. Why I give it a rolling moment? So a pitching moment to make the aircraft tendency back, the nose back down, right? Now that is a negative pitching moment. Why? Again, back to the right-hand rules, right? So if that directions where the y-axis positive to the right wing of your aircraft, so which is the other directions, then obviously that going in towards the towards outside of the board, then obviously it's going to be a negative, right? Now, if the other conditions like this, obviously that will be the opposite, right? So if your lift is slightly forward to the CG location, then that pitch moment will then make the aircraft tendency to pitch in that direction. So whenever you got the gust, the aircraft, rather than putting back to the other direction, the opposite direction, it will then keep moving up and up until you have unstable condition. So this is considered as stable. This is considered unstable. By looking at two positions of those two forces, which is the weight and your lift. Now, obviously, we could say that one indicator for longitudinal static stability for a conventional aircraft, remember, we're talking about only a conventional aircraft, the CG position must be always ahead of aircraft aerodynamic center. So ahead means here is that closer to the nose, right? So the CG must be closer to the nose compared to the aircraft aerodynamic center. Now, in this case, for a positive increase of alpha, so if you have a positive increase of alpha, obviously this is alpha, and it's a positive increase, the aircraft should generate a negative, remember the right-hand rule, a restoring pitching moment. In this case, that we talk about Cm alpha, right, which is dCm d alpha. That is the mathematical expression for that. But in layman terms, the expression is that the change of pitching moment due to the change of alpha, right? That's how you say it. So it means that if you alpha change positively, then that Cm should be changed negatively because to give a tendency of pitching down, right? So that's why this dCm d alpha should be negative. For a positive change of alpha, dCm should give you a negative tendency. That's why then if you put them together as a mathematical expression, dCm d alpha should be negative. So it should be less than 0, right? So that is kind of like way to say it, like your aircraft need to be always to be statically stable longitudinal. It must be the CG position must be closer to the nose compared to the aircraft aerodynamic center. But in mathematical expression, that means Cm alpha should be negative, right? So if the CG exactly at the location of aerodynamic center, which is imagine that green forces right the same location at the blue forces, which is your weight, then obviously whatever happens with the tendency or alpha, there is no it doesn't have a tendency to put it back because obviously that forces is right at that CG location. That is when the neutral stability happens, right? So the neutral stability happens. That when that's why it always says that that point, we call it as a neutral point. We're going to talk about neutral point later on, so don't get confused about that. So you can consider that if the CG coincide with the aircraft aerodynamic center and then the neutral conditions happens, then that point, we call that as a neutral point. Okay, now if you look at that a very simple way like this, then remember that CG has to be ahead of our aircraft aerodynamic center in order to make it as longitudinal stable. So if you measure the distance of your neutral point, which is in this case I put it as an x and p, but it basically is the location of your aircraft aerodynamic center. And then XCG, if you measure it from the nose, we call it XCG. So in order to the aircraft set to be statically stable, if a delta lift or the additional lift applied to your neutral point, then that point has to be behind the center of mass or the center of gravity of your aircraft. It means that, as I said, that center of gravity should be closer to the nose compared to the aircraft aerodynamic center, right? So if you put it that in the very simple equations or mathematical expression, it means that x and p minus x and g should be always positive, right? Because that should be greater than xcg if you measure it from the nose, right? So if you now sometimes in the expressions we want to put it in the non-dimensional, and you could divide it that with your mean aerodynamic center, right? Or sorry, mean aerodynamic chord, which is the distance of your where the lift, additional lift acting. In this case, I term it as a x and p minus xcg divided by the mean aerodynamic chord should be greater than 0, right? So from a condition defined in this statement, it means that your static stability implies a positive static margin. That means your aircraft should always have a positive static margin if you define this as a static margin, right? So if you have aerodynamic coefficients already derived for your aircraft, and then you know what Cm alpha is, right? Now, from previous slide, we know that in order for your aircraft to be statically stable longitudinal, that Cm alpha should be negative, right? Or if you want to calculate the static margin, that static margin is basically minus Cm alpha divided by CL alpha, then your static margin could be calculated by Cm alpha divided by CL alpha. But remember, the sign is negative because of what? Because Cm alpha is always negative. If your aircraft statically stable, Cm alpha should be negative. Now CL alpha should be always positive, right? Because if you draw that, if I could draw it here, CL alpha curve, if this is CL, this is CL, this is alpha, this is CL, then your CL alpha curve is always like that, right? So your CL alpha is change of CL due to the change of alpha. The slope is always positive. If you design a conventional aircraft, that your CL alpha curve should look like. It will not look different, right? So CL alpha is always positive. So Cm alpha is always negative. CL alpha is always positive. So the static margin is minus Cm alpha divided by CL alpha. That should always be positive, right? Based on our definitions here, if your aircraft need to be considered as statically stable. Okay, right. So now there is a notation or definition of pitch stiffness. Basically, pitch stiffness look into how good is your longitudinal, static longitudinal of your aircraft. Now we agree that Cm alpha, in order to be stable, it has to be negative, right? So if you draw your Cm alpha curve, is always like that. So we are looking into this graph there, right? So that is when Cm alpha is negative, right? So sometimes the graph is not really non-linear like that. Sometimes it's always quite linear like that, for example. It doesn't really matter. But if you assess your aircraft aerodynamics, later on you will see that Cm alpha sometimes goes like that, right? So if this aircraft is stable, your Cm alpha is always make a negative slope like that. That is when Cm alpha is negative, right? So there is a condition where the aircraft is unstable, your Cm alpha is positive like that, right? So now how good it is or how stiff is your pitch stability or longitudinal stability is obviously related to the slope is there. So your slope could be either like that, it could be either like that, it could be even more stiff like that. That is the stiffness is more stiff your longitudinal stability is. So you could then relate that how fast it is to make a tendency to put your nose down back. If your aircraft is less stiff, and obviously it will like a sluggish movement, to put your aircraft back down, which is obviously will sometimes could introduce the very quick into moving into the dynamic stability. We're going to talk about dynamic stability, hopefully, if we have time, but of course, as I said, it will be delivered in the level 7 stability and control module if you go into level 7 later on. Right, so in the first case where CM alpha is negative, the moment following the disturbance is negative, tend to restore alpha to equilibrium value, which we have already agreed. But in the second or later case, when CM alpha positive, the moment following the disturbance is positive and experience a force that drives it away from the equilibrium, which is unstable, right? The condition for pitch stability, we have already agreed, should be CM alpha should be always negative. So when CM alpha equals 0, nor positive or negative, and then obviously that is when we could tell that is a neutral point, which is the aircraft becomes a neutral stability. Okay. Now, let's have a look at the equilibrium what we're talking about. Okay, so the lift is mainly produced by the wing, as you know. So you have the lift from the wing, LW there, right? And then you have also the lift produced by your tail, which is LT over there. Now, the pitch torque is the sum of the torque originated by the lift from the wing and lift from the tail. And of course, the moment, the pitching moments, inherent pitching moments already there, which is the M0 wing body, right? So if you talk about the equilibrium of moment on the or around the CG, which is over there, then obviously that moment is basically the moment created by the lift from the wing, the moment created by the lift from the tail, and also the moments inherently there, which is the moments already based on the when alpha is 0, created by the wing of the body. So if you analyze the aerodynamics, you always know that apart from the lift, your airfoil, for example, is also has a moment. Now that moment it's the inherent moment, pitching moments already there because of the existence of the airfoil of your wing and body of your aircraft, right? Now, obviously, in steady state, we know that sigma f should be 0, right? And the moment around CG, or sigma moment, should also be 0. You follow? So in this case, obviously, if we talk about or we look into the sigma force in Z direction here, so we know that the lift plus the lift from the wing plus lift from the tail should equal to W. So that is the sigma F, right? Now this one is the sigma moment, which is sigma moment around CG, which is the inherent moment already there, which is M0 wing body, plus LW plus LT multiplied by delta L, which is delta L is the distance between lift from the wing to the center of gravity, minus LT, which is the lift from the tail, multiplied by the distance LT. I hope you understand why actually that is there, right? Because obviously if you look at the coefficient, the sigma m, which should be equal to 0, then m m0 wb, which is wing body, plus l from the lift multiplied by delta L, the distance. But of course now LT should be multiplied by this distance, right? Which is obviously that distance is LT minus delta L, right? So when you rearrange that, then that becomes that equation, okay, that where delta L is basically xcg. Remember the xcg, which is the distance from the nose of your center of gravity minus the distance of your lift, where your wing of your lift, where your lift of your wing acting, that is your delta L, which is eventually this is what we defined earlier as your static margin. Remember that? So I hope you understand why. So there is a simplified, we call it a simplified longitudinal equilibrium. Right. So I hope you understand the all the notations there and why is there, because of simply from we try to make it a sigma f and sigma m equals to 0 in the steady state condition. Right. Now let's have a look at a little bit more complicated by looking into this. Now if you look at that a bit more complex in that, so if you're talking about the total moment around CG, and obviously you have the moment of the, I mentioned about the aerodynamic, because of the aerodynamic center, the pressure, the center of pressure to the aerodynamic center of your wing and fuselage. You have the moments already, we call it moment aerodynamic center of wing and fuselage, plus the lift, which is lift, wing, and fuselage over there, multiplied by the distance. Remember, the distance is xcg minus x aerodynamic center of wing and fuselage, which is that distance over there, right? So that distance, which is n xcg minus xac wf. But now we still consider if there is an alpha increase, so we consider that is also cos alpha minus. Remember, the sign is plus minus. If you're going that way is positive, but if you're going that way is negative. So the lift from the horizontal tail will give you a minus or negative moment, because it's going to go that way, right? So minus lift of your horizontal tail. Now the distance is obviously x, your horizontal tail, which is xac subscribe h, minus xcg. Obviously we're talking about this distance now, which is, if I draw that like again, that is that distance, which is xac minus xcg, right? Now because there will be a different angle of attack between the tail and the wing, because of the wake turbulence of the wing. So the wing is obviously gives some wake turbulence to the tail, then that alpha is not the same as alpha happens to the wing. Then that usually we corrected it into with the term epsilons there, which is the downwards angle due to the wing weight, right? Now if you look at that further, if you put it in the coefficient form, again, as I mentioned, now we start talking about the coefficients form, which moment is basically half rho v square s cm, and then you multiply that. In this case, we use c, which is the mean aerodynamic center. This is obviously half rho v square is what we call it dynamic pressure q, which is this one. So we talk about now the moment around CG is basically half rho v square or q at the wing multiplied by the s and then by the cm coefficient of moment, pitching moment. Remember, m is the pitching moment, and then multiplied by the c equals to, well, this is when we talk about the inherent moment at CG plus the moment caused by the lift from the wing, which is we express it in here, and then the moment caused by the tail, right? Now, in most cases, alpha is always assumed small. So in this case, that's why then the cos alpha earlier from the earlier previous equations disappear. Well, it's equals to 1, obviously it becomes disappear. Then as well as also cos alpha minus epsilon on the last term of the previous equation, right? So from here, so it's also equals to 1 if you consider the alpha is always small. Now we have to also make a note that whatever happens on the wing is not always the same whatever happens on the tail, because of that downwash or wing wake we talked earlier. So when we talk about dynamic pressure, so we should then say that the dynamic pressures on the wing is quite different from the dynamic pressure on your horizontal tail. Okay, so that's why the dynamic pressure at the horizontal tail plane is not equals to dynamic pressure of the wing, but is equals to what we consider that as a dynamic pressure on the horizontal tail. Right. So if you divide this equation by these factors, which is dynamic pressure on the wing multiplied by S multiplied by the mean aerodynamic chord of your wing, then obviously that all disappear. Apart from that, that's what you left with. Then obviously that is also left by that. Then this one obviously becomes that fact. Well, this is disappear as well. This is disappear. Then what you left with is this one. Then this one is then divided by the CW, which is the mean aerodynamic chord of your wing. And then the same as this. Now remember, because QH is not the same as QW, then that should stay QH, QW, and then that S, the horizontal area of your horizontal tail plane, divided by horizontal, the wing area S, and then that still stay CLH, which is there, but and then that one again also divided by C. W, which is mean aerodynamic chord of your wing. Now, the terms of QH divided by QW, sometimes they call it a dynamic pressure ratio, which is makes sense, which is the pressure ratio, dynamic pressure of the horizontal tail divided by the dynamic pressures of the wing. That is why they call it as a dynamic pressure ratio at the tail, or sometimes they call it also tail efficiency factor. So, is it epsilon? Is it this one? Or eta, sorry, eta, which is tail efficiency factor. Now that typically varies between 0.8 or 1.2. So you could make assumptions if you want. For the first time in practice, is normally determined using the wind tunnel test, but obviously in the aircraft design, for example, you could just make assumptions whether you take it between 0.8 to and 1.2. Right. Now the next term, which is this one, right? So we talk about the term of this, which is, I put it over there, SH minus S multiplied by the distance of your your horizontal tail plane to the nose minus the distance of your CG, XCG, divided by the mean aerodynamic chord of your wing, or sometimes simply denoted by that, which is LH. LH is obviously here, this one. You could then deduct it straight away. Now, this is, they call it a tail volume ratio. It's the ratio of the two volume characteristic of the aircraft geometry, wing versus your horizontal tail plane, right? So now the LH, which is the distance between your tail to the CG, is quite different from the LT, which is from previous simplified diagram, which if you go back to the slide 15, but sometimes the difference is very small in practical term. So bear in mind that we talk about LT is basically the distance between this to, I think if you have clicked through back to the slide 15, which is this one. So remember the distance, LT here is the distance between horizontal tail plane to the wing. But here we talk about a different, which is the distance between LH or the tail in slide 15 to the CG, not to the wing. But obviously, as I said, it's quite different from the LT. Now, for a better representations of lift coefficient, sometimes we also, CL of is basically CL alpha dot alpha. Now, for the wing and fuselage, we could also do that, which is the CLD alpha times alpha, right? And for the tail, we could also do the same. Now, if you go back to the kind of like a complete equations before, where the alpha horizontal tail plane is different from the alpha that happens on your wing due to the downwash there. And then IH is your incident angle, where your tail set in the beginning the angle between your the mean chord line of your horizontal tail with the fuselage datum line. That is the incident angle. Then you could then consider or you could make the approximations where the downwash is basically the initial downwash plus the change of the downwash due to the alpha change, which is, I think, I remember I noticed in Mo's lecture note or aircraft design, he could take that one single value, not remember how it is or what it is, but you could consider the angle of attack happens on your horizontal tail, which could then be simplified, or we could then written in this kind of expressions, right? And then from equation 4, which is the previous equations, this one, you know that CLH, which is CL alpha horizontal times alpha horizontal, then you know that alpha horizontal is this equations, then you could then multiply CL alpha horizontal with these expressions over there, right? So I think it's the time now. I'm going to slightly continue. I think it's about like 10. We look into the case in the tutorial sessions, which is already covered what we discussed today. So I hope we could answer that questions in the tutorial sessions. And then I kind of like slightly continue to summarize what we discussed about this longitudinal static stability, as well as then we discussed briefly about the lateral static stability, and as well as also directional static stability. Okay, any questions?